This video is about how we can use combinations of the Maclaurin series expansions to expand more complicated expressions. So we're going to do 3 examples. The first one is this one. So we're told to ignore any terms of x to the power 4 and above. That's what this is saying here. Given that terms in x to the power n, where n is greater than or equal to 4, may be neglected. So I'm going to ignore x to the power 4, x to the power 5, x to the power 6, and so on. I need to use the series expansions for e to the power x and sine x to show that e to the sine x is roughly the same as 1 plus x squared over 2. So, the sine x on the inside here, I can replace that with x minus x cubed over 3 factorial. I can ignore all these higher powers because I was told to in the question. So I am going to write e to the power of x minus x cubed over 3 factorial, which is 6. So I've just replaced the sine x with the first 2 terms of the sine expansion. In order for me to use the e to the x expansion, to make this simple for myself, I'm actually going to split this into 2 using index laws. I know that e to the power x is the same, I know that e to the power x minus x cubed over 6 is the same thing as that. If I expand e to the x, I'll get 1 plus x squared over 2 factorial plus x cubed over 3 factorial. And again, I can ignore the power 4, power 5, and so on. So I have just written this out with the expansion from down here. I'm now going to do the same thing with this, but obviously instead of the x on the inside, it will be minus x cubed over 6. So I've got 1 minus x cubed over 6. And the next term would actually be minus x cubed over 6 all squared over 2. But I know I'm not going to include that because that would give me a power 6 term, which I'm supposed to ignore. So let's get rid of that. I don't need to include that term. All I'm going to do now is expand all of this. So I would have all of this times 1. And then I'm going to have the 1 times the minus x cubed over 6. And I'm not going to do any more expansions because the next term, the x times the x cubed over 6, would give me an x to the power 4, which I've been told to ignore. Now just collecting these last 2 terms together, you can see they're going to cancel out. And so I get my answer. So e to the power sine x is approximately, it's not equal to, it's approximately equal to 1 plus x squared over 2. It's approximately equal to because I did ignore x to the power 4, x to the power 5, and so on. Here, I'm asked to work out the series expansion for cos 2x squared. So to do this, I'm going to take the cos expansion, which is 1 minus x squared over, it's this thing here. But I'm going to be substituting 2x squared into that. So I would have 1 minus 2x squared over 2 factorial plus 2x squared to the power 4 over 4 factorial, and so on. Simplifying this then, the 2x squared times 2x squared gives 4x to the power 4. the 2x squared times 2x squared times 2x squared times 2x squared gives 16x to the power 8. And then we can simplify those. And so on. Right, last example, and it's a bit trickier. And there's two parts to this. We need to first find the first three non-zero terms of the series expansion of ln of root 1 plus 2x, all divided by 1 minus 3x. And we need to state the interval in x for which the expansion is valid, because the expansion is not always valid for logarithms. So, the way this is written at the moment, I can't use this expansion at all. So I want to rewrite this. Now, I can use the laws of logarithms to split this up. I could say that ln of root 1 plus 2x, all divided by 1 minus 3x, is the same thing as ln of the square root of 1 plus 2x minus ln 1 plus 3x. Remember, ln a over b is the same thing as ln a minus ln b. That's the rule I've just used here. Now I still can't quite use the rule yet because I've got this square root. But that's okay because I know I can rewrite that as a power of a half. Which will then allow me to use the power laws of logarithms to bring that half to the front. Now I've got to the point where this is in this form and this is in this form. So now I can use these series expansions. So let me create some more room. And we're going to do these two things separately. And then take them away. So the first one we had, the 1/2 ln 1 plus 2x, will be 1/2 of. So we're using this expansion, but we're substituting 2x in instead of the x. So I would have 2x minus 2x all squared over 2 plus 2x cubed all over 3, and so on. I'm just doing the first three non-zero terms, which when I simplify that is going to give me x minus x squared plus 4 over 3x cubed. Now to work out the second logarithm that we had, which was the ln 1 minus 3x. Again, we're using this expansion, but instead of the x, we have minus 3x. So we're going to have minus 3x minus 3x squared over 2 plus minus 3x cubed over 3, and so on. Which simplifying will give minus 3x minus 9 over 2x squared minus just 9x cubed. So we have expanded this and got this. We have expanded this and got this. And remember that we want to take those two things away from each other. So I want to do all of this minus all of that. So x minus 3x is 4x, minus x squared minus 9 over 2x squared is plus 7 over 2x squared. And then finally, the 4 over 3x cubed minus 9 x cubed is going to give plus 31 over 3x cubed. And there we are. We have the first three non-zero terms of this expansion. Part A done. The next, we have to state the interval for which this expansion was valid. So for what values of x is this actually worthwhile doing? Which values of x are we actually allowed to do this for? So, remember that our expansion is only valid if this is true. Now, in the first expansion, we didn't use x, we used 2x. So the first expansion is only valid if 2x is greater than minus 1 and less than or equal to 1. Therefore, dividing through by 2, x would have to be between minus a half and 1/2. If x is between those values, then our first expansion was valid. The second expansion, however, is only valid if minus 3x is bigger than minus 1 or less than or equal to 1. Dividing through by minus 3 now. Remember, dividing by a negative is going to flip the signs. So dividing through by minus 3 flipped that there. Excuse me. So the second expansion is only valid when x is between minus 1/3 and 1/3. So obviously for the overall answer to be valid, I need to choose the more restrictive of the two restrictions. Because if this yellow box is true, if x is between minus 1/3 and plus 1/3, then this is also going to be true. So both of the expansions would be valid. If I were to look at the top one, then if x was, for example, 0.4, then the top expansion would be valid, but the bottom expansion would not be. Therefore, the whole expansion would not be, because they both need to be valid. So ignore that and focus on the more restrictive of the two sets of values. And there we go. So that's how you can use combinations of the Maclaurin series expansions to expand more complicated functions.